This is a short video on finite state machine string pattern matching. The problem we're trying to solve is, how do we match a string or pattern with a set of input characters? As you might remember from first year, finite state machines directly translate to regular expressions. This allows us to use them to match string patterns efficiently and recognize regular expressions as well. This is a quick reminder of the formal definition of a finite state machine. We have Q, the set of states, Q0, an element of Q that is the initial state, A, which is a subset of Q, which is the set of accepting states, sigma is the input alphabet, and delta is the transition function. This is the same as a 2D graph of states with transitions between the states represented by arrows with symbols over them representing the characters that cause the transition. Constructing the DFA is computationally complex. It takes a minimum time of the length of the pattern times the size of the alphabet. It's generally built by constructing an NFA for the pattern and converting it to a DFA using power set construction. However, once the DFA is built, it's very fast to use and only takes the order of the input length, as each character causes one state change until the last character is consumed and you have your answer. Using the DFA is exactly the same as using a regular DFA. The pseudocode, taken from the lecture slides, is quite simple. It involves going through the input and setting the current state to be the transition from the current state with the current character. It then outputs if it is currently in an accepting state, which means that a pattern has been found. This just describes the operation of a regular DFA, though in the following examples there is the caveat that arrows for all other letters are missed out, to save having to draw many arrows back to the first state. So here's an example. Does the string CACAT have the substring cat in it? And here is a DFA to recognize cat. We start off in the first state with the empty edge connecting to it. The first character read in is a C, which takes us to the second state, and then an A, which takes us to the third state, another C which takes us to the second, an A which takes us to the third, and then a T which takes us to the accepting state. This means that cat is a substring of CACAT. Another example, does the string CARC have the substring cat in it? Again, we start in the first state on the left, follow the C, then the A, then we encounter an R, which means as there are no edges, go back to the first state. Then we follow the C we read in. At no point did we reach the accept state, which means that CARC does not have the substring cat in it. So that's it for this video. There's not really a lot to finite state machine string pattern matching, and I hope you enjoyed it.